So in the setting of Euclidean spaces, I have two videos where I prove that the length of a curve defined as you see here equals the integral of the speed of the curve. Now, the integral of speed of a curve is not easily defined for arbitrary metric space targets, but the definition through supremum of course does make sense, as you see here. So if gamma is a curve in this metric space, which is defined to be a function, then its length is the supremum of summation of distances of consecutive nodes, where the supremum is over all a natural number n and all choices of partitions of the interval into n subintervals. The immediate observation is that if you connect 2 points by a curve, then the distance of the points is never more than the length of the curve connecting them. So it's actually easier to write than say. So length of this is always bigger than the distance of gamma b from gamma a. So the proof is satisfyingly easy. So you take n equal 1, and then there is only one possible partition, so t0 is a, which is less than t1 equal b, and well, supremum is bigger than a particular element. Now, the reverse of this then becomes an interesting question, and it is not always possible, of course, but then you wonder what spaces have these properties that you can reverse this inequality. So the geodesic metric space is one where every pair of points, so for every pair of points x and y in your space are joined by a curve such that the distance of x from y equals the length of that curve. So if the distance is always realized as a length, so examples of course will be any Euclidean space. So you have any 2 points, and the distance is actually the length of the line that connects them. So this is your curve gamma, its length equals the distance of them. Non-example is that so let's say you have your metric space is a subset of R2, and it's something like a bent object. So this curve is your metric space x. So with the distance is just the Euclidean distance, okay? So that distance of this point from that is just the distance that would be in a Euclidean R2. But in this case, because your metric space is not all of R2, there isn't actually any curve with exact same length as the distance of the 2 points. As you can see here, it's pretty easy to break the space being geodesic. So now a weaker condition than being geodesic is the notion of length space. This is where you don't actually get a curve with the same length as the distance, but you get pretty close. So we have to be very precise in this. So given xy, any xy in your metric space, the distance of x from y is the infimum of the length of curves that connect these two So infimum over all curves joining x to y. Now an example of this space could be you have R2 and you remove just 1 point with the usual distance. Then what happens is you have your space again, but then there is this red point that is not even part of your space. Then if you have 2 points that would have been connected by a straight line, now it's impossible. You have to avoid that red dot. It's not in your space. You have to make a tiny loop around it and connect. Now if this is your curve gamma, then its length is very close to the distance of xy, and then you can find the sequences of gammas which in limit do have length converging to d of xy. But per se there isn't one single curve with length exactly equal to the distance of these points. So we can see that the geodesic spaces of course are length spaces, so you get the infimum actually right away from one curve. And these spaces have some properties that generic metric spaces don't, especially the geodesic ones do come up a lot. And so some fun with curves and the length and the distance.